Project leaders working with the National Norwegian Aviation Museum in Bodø framed the mission in practical terms. Locate the Blackburn Skua L2896 and hoist the airframe from the Fjord floor to the surface for long-term preservation. This aircraft served with 803 Naval Air Squadron, the fleet air arm of the Royal Navy. It was lost during a strike mission aimed at the German capital ship Scharnhorst. Following an engine failure, the bomber ditched into Orkdalsfjorden in Norway. The operational stakes for this forensic recovery are dictated entirely by a single environmental metric. The target wreckage rests on a steep underwater slope at a depth of 794 feet. At that depth, direct diver intervention was not feasible for this operation. Conventional diving teams could not reach the seabed to secure the airframe. Every recovery procedure must bridge a massive vertical column of dark freezing saltwater. During the initial ditching event, the pilot and observer survived the severe hydrodynamic impact with the Fjord. The Blackburn Skua had an enclosed cockpit canopy. To survive the rapid sinking sequence, the pilot and observer had to find the release and force their way out as the aircraft flooded. They had to get clear of the airframe before it was pulled under. Once they escaped, the waterlogged bomber descended to the bottom of the deep coastal shelf. The crew swam to shore and were captured, while the specific resting position of their aircraft remained unverified for years. The search operation required systematic mapping of the underwater topology. In 2007, survey teams used sonar to sweep the deep sections of the fjord. The returns eventually isolated an acoustic anomaly consistent with the footprint of an airframe. To verify the target, the team deployed remotely operated vehicles down to the seabed. The camera feeds illuminated the dark zone and confirmed the identity of the target. On video, the aircraft appeared to be resting relatively upright on the slope. Under the lights, the main fuselage, cockpit area, and wings looked largely intact. Locating the wreckage solved the initial localization problem, but it immediately initiated a severe engineering constraint. The recovery operation had to transition from a survey profile to a heavy lift profile without putting divers in the water. Retrieving submerged machinery from deep water requires precise load distribution across intact structural ribs. A standard recovery plan relies on divers to assess the underside of the wreck, clear away accumulated sediment, and wrap lifting straps directly under the primary load paths of the wing roots. Because the depth of 794 feet acts as a hard physical barrier to human hands, the extraction plan had to rely exclusively on robotic rigging. Operators stationed on the surface vessel had to fly remotely operated vehicles down the water column and manage long umbilical cables. The physical distance between the control room and the target required the surface team to account for deep water currents pushing against the umbilicals, which constantly threatened to drag the small vehicles off course during delicate maneuvers. The technical decision to rig the aircraft using only mechanical arms introduced a significant hazard control problem. Threading thick industrial slings under a dormant airframe without snagging delicate control surfaces requires deliberate pacing and continuous camera alignment. The surface operators faced a restricted field of view, relying entirely on flat video monitors to judge physical distances in a low visibility environment. The decision to execute a blind lifting operation meant that the team had to guide the heavy straps into position using only thrusters and hydraulic pinchers. No human diver could provide tactile feedback regarding the tension of the straps or the condition of the metal skin resting in the mud. Operating mechanical pinchers near fragile aviation components requires extreme precision to avoid punching through the outer skin before the lift even begins. How do you rig a lifting cradle around a submerged World War II bomber when divers cannot reach the seabed to touch it? For 68 years, the deep fjord environment silently erased the structural strength of the submerged bomber. The loss sequence began on the 13th of June, 1940. The strike package engaged the target, but during the egress phase, this specific aircraft suffered a total engine failure. Later examination of recovered components was consistent with a serious restriction in the fuel feed. A starved radial engine quickly ceases to produce thrust, rapidly converting the aircraft into a heavy glider. The pilot faced an immediate operational constraint. With altitude dropping rapidly and no safe runway within glide range, the crew had to trade altitude for airspeed to maintain control authority just long enough to execute a controlled water landing into the fjord. The shift from stable flight to a hard water touchdown loads the airframe with brutal stress. The physical transition from stable flight to an abrupt water touchdown generates massive structural stress. On impact, the Bristol Perseus tore free and tumbled down into the deep. With the engine gone, the wreck's balance and buoyancy changed. With the engine gone, the airframe stayed afloat just long enough for the two men to break free. Then it flooded, lost its last buoyancy, and began the long drop toward the deep mud slope. Once the aircraft settled onto the underwater shelf, a continuous chemical process took control of the wreckage. The engineering team analyzing the site decades later had to account for severe material degradation. The Blackburn Skua featured an airframe constructed extensively from duralumin, an early high-strength aluminum alloy. To handle intense flight loads, the original aircraft designers integrated heavy steel fittings at critical junctions, including wing roots, tail connection points, and control surface hinges. Placing these directly connected metals into a cold, saltwater bath initiated a massive galvanic corrosion trap. The physical environment could rapidly weaken the duralumin around steel fittings, sometimes leaving the steel comparatively less affected and producing a hidden, highly dangerous structural hazard. Saltwater functions as a highly efficient electrolyte when two dissimilar metals remain in direct physical contact. Because aluminum is a chemically active metal compared to steel, the entire skin and internal ribbing acted as a sacrificial anode, continuously surrendering electrons to the heavier steel hardware. This relentless electrochemical reaction dissolved the core strength of the lighter metal from the inside out. The primary hazard for any future recovery effort lay in the visual deception caused by this specific type of decay. Unlike rusting steel, which often signals its damage on the surface, corroded aluminum can look intact on camera while losing strength beneath the skin. The outer skin panels, protected partially by original factory paint and a layer of marine mud, presented a misleading profile to the remote cameras. A fuselage section that appeared completely solid on a surface monitor was dangerously brittle. The continuous anode effect meant that the internal metallic lattice of the lower fuselage longerons had been hollowed out on a microscopic level. The structural reality of the airframe fundamentally altered the available recovery margins. Every crossmember and bulkhead connecting the tail section to the main fuselage had spent decades submerged, quietly sacrificing its mechanical mass to the surrounding steel bolts. The remaining structure resting in the mud was little more than a fragile shell mimicking the shape of a combat aircraft. If the aluminum skin is effectively hollowed out by 6 decades of galvanic reaction, how much dead weight can the lower longerons actually support? By 2007, sonar sweeps narrowed the fjord down to a single airframe-sized hit. 794 feet down, no diver could touch it. Operators had to rely entirely on unmanned submersibles. Remotely operated vehicles descended through the dark water column to illuminate the seabed and confirm the identity of the wreckage. Under the ROV lights, the Skua still looked like an airplane, upright, canopy, and wings unmistakable. The feeds gave the surface crew a clean layout and orientation. However, relying purely on optical sensors creates a dangerous operational blind spot. Video monitors display geometry, not structural density. The cameras could confirm the presence of the airframe, but they could not peer inside the metal to assess the true condition of the internal structural ribs. The lingering hazard of a galvanic corrosion trap meant the visual data was fundamentally incomplete. Seeing the bomber was only phase 1. Now the team had to turn that sighting into a load path, using the same ROVs to place slings and build a lifting cradle from the surface. Sling placement became a slow choreography. The tether bowed in the current, and the pilots fought to hold a hover inches from the skin. Using hydraulic manipulator arms, the vehicles must physically thread wide synthetic lifting straps beneath the wings and center fuselage. The operators manipulate these arms while looking at flat, two-dimensional screens. They lack any tactile feedback to tell them if a strap is sliding smoothly over a solid bulkhead or grinding against a brittle section of the lower skin. Routing lifting slings beneath a wreck like this means working slowly against mud, low visibility, and a fragile airframe. From the surface, the ROV teams inched webbing into position under the strongest surviving structure they could reach, keeping clear of delicate control surfaces. Progress came in small, careful steps, with repeated checks from multiple camera angles before committing the lift geometry to the hoist plan. With the sling seated, the lifting cradle was complete and ready to take load. The Skua's outline was certain, its strength was not. On the 8th of April 2008, the recovery window finally opened. A specialized crane barge maneuvered over the precise coordinates in the Norwegian Fjord to initiate the mechanical extraction of the Blackburn Skua. Transitioning from a static underwater survey to an active heavy hoist requires a highly controlled handling plan. The surface crew held station directly above the wreckage using careful station keeping to limit drift and surface motion over the lift line. The operational objective shifted entirely to bridging the vertical column of water between the barge deck and the seabed without destroying the fragile historical evidence. The surface team deployed the massive primary lifting cable from the crane, sending the heavy steel hook slowly down into the darkness. Because human divers were prohibited by the extreme depth, the final critical connection relied entirely on the robotic rigging systems already in place. The remotely operated vehicles had to visually acquire the descending crane hook and carefully guide it toward the master lifting ring. This heavy metal ring gathered all the individual synthetic straps that had been previously routed beneath the wings and center fuselage. Securing this master ring to the main crane hook established the single continuous load path necessary to pull the airframe from the deep mud. Once the physical connection was locked, the heavy lift supervisor faced an immediate environmental hazard. Wind and surface swell could translate into sudden load changes down the lifting cable. To reduce those shocks, the lift plan emphasized slow, steady winch movements, constant monitoring of line tension, and careful timing against the surface motion, smoothing the load rather than letting it snap. With the wave hazard mitigated, the crane operator began the highly sensitive process of transferring the load. The initial pull sequence is never designed to lift the wreckage immediately off the bottom. Instead, the winch slowly takes up the slack, gradually pulling the synthetic straps tight against the underside of the wings. This specific phase of the operation forces the dormant structure to undergo a massive redistribution of physical forces. When the aircraft rested safely on the deep mud slope, the solid ground evenly supported its entire dimensional length. Hoisting the airframe strictly by the center section fundamentally changes how gravity and weight act on the metal structure. The central lifting straps become the exclusive source of upward force for the entire aircraft. Consequently, every structural component extending past those central straps transforms into a heavy, unsupported beam. This geometric reality introduces the tensile failure boundary constraint. The long tail section of the bomber was completely filled with cold seawater and dense marine sediment, adding thousands of pounds of dead weight to the rear of the aircraft. The tensile failure boundary defines the exact moment when the immense downward pull of that waterlogged tail exceeds the remaining internal strength of the corroded fuselage bulkheads, connecting it to the lifting cradle. The engineers in the control room closely monitored the digital tension gauges on the main winch. Before the aircraft could physically leave the bottom, the crane also had to overcome the powerful suction effect of the deep fjord mud holding the fuselage in place. Breaking the suction requires a slow, steady increase in lifting force rather than a rapid upward pull, preventing the airframe from springing upward unpredictably when the mud finally releases its grip. The operation reached the critical threshold where the mathematical planning of the surface team met the hidden material reality of the sunken bomber. As the crane begins to take up the slack, the dead weight of the waterlogged Skua transfers entirely to those specific sling points. The physical transition from the seabed to the water column forces a strict mechanical trade-off. A centralized lifting cradle can successfully elevate the mass of the main fuselage, but it cannot reinforce the unsupported extremities of a compromised airframe. The main winch of the crane barge initiated the primary vertical pull, lifting the Blackburn Skua from its resting place at 794 feet. As the heavy mud suction finally released its grip, the complete weight of the waterlogged bomber transferred instantly to the synthetic straps. The main fuselage and the wings were supported directly by the robotic rigging, allowing them to remain mechanically stable as the long ascent began. The rear of the aircraft extended dozens of feet behind the rearmost lifting strap. This geometric reality subjected the aft fuselage directly to the tensile failure boundary. Behind the last strap, the tail hung heavy with mud and trapped freezing seawater. The structural connection between this massive suspended weight and the supported central fuselage relied exclusively on a series of internal lower longerons and metal bulkheads. At those joints, decades of dissimilar metal corrosion had already done the killing. What remained was a paint-skinned shell, its internal lattice dissolved from the inside out. As the heavy aircraft cleared the seabed and hung suspended in the dark water column, the dead weight of the sediment-filled tail applied massive downward shear forces against the severely weakened junction. Despite efforts to raise the aircraft as gently as possible, the tail section broke off during the recovery and fell back to the fjord floor. The sudden structural failure caused a rapid shift in the center of gravity for the remaining wreckage. The abrupt shedding of thousands of pounds sent a massive dynamic shockwave straight up the long steel lifting cable to the surface barge. Despite the mechanical shift, the primary lifting straps maintained their grip on the heavy wing roots and the forward section. The engineering team on the surface had to continue the hoist without pausing or reversing the winch. Reversing the winch would create slack in the synthetic straps, which could allow the remaining aircraft sections to slip entirely out of the lifting cradle. The crane operator carefully managed the ascent speed to prevent hydrodynamic drag from tearing the remaining wings away from the central roots. Pulling a large flat object vertically through hundreds of feet of water generates immense fluid resistance. Every foot of upward travel added stress to the surviving metal joints. The surface team maintained a slow, continuous pull until the distinct shape of the greenhouse canopy finally broke the surface of the fjord. The recovery crew maneuvered the crane to swing the surviving sections over the open deck of the barge. As the wreckage left the water, the team faced another immediate physical constraint. Water trapped inside the hollow wings, and the forward cockpit was no longer buoyed by the surrounding fjord, meaning the relative weight of the suspended object increased dramatically the higher it was lifted into the air. The crew had to pause the hoist just above the deck to allow hundreds of gallons of trapped seawater to drain through the lower access panels before carefully lowering the historic artifact onto the wooden support blocks. The visual inspection on the deck confirmed the mechanical consequences of the underwater environment. The clean break at the rear of the fuselage demonstrated exactly how the hidden degradation dictated the partial outcome of the lift. The fuselage, the forward cockpit, and the inner wings were successfully salvaged. The recovery team had retrieved the primary crew stations and the central structural core of the bomber. The main section is secured on the barge, but the heaviest piece of the original aircraft is still missing in the dark. 3 years after the primary airframe was secured, a specialized oceanographic research vessel returned to the Norwegian marine environment to locate the heaviest missing component of the Blackburn bomber. In 2011, the research vessel Gunnerus returned to the fjord to search for the missing Bristol Perseus engine, using shipboard survey gear and an ROV to work at depth. The target was the original 905 horsepower Bristol Perseus engine. During the initial ditching event, this massive block of metal separated from the aircraft and became subject to strict steep slope debris migration. When a highly dense, non-buoyant object detaches underwater over an inclined seabed, gravity forces it to tumble continuously down the geological gradient. The heavy radial engine did not stop near the touchdown point of the main fuselage. Instead, its sheer density caused it to roll hundreds of yards further down the submerged coastal shelf until the terrain finally leveled out in the deep basin. The survey team tracked the engine to a final resting depth of around 1,200 feet, roughly 370 to 375 meters. This extreme depth required a separate extraction operation, using an ROV to rig straps beneath the engine and a crane on the support vessel to lift it clear. Unlike the fragile aluminum airframe, the solid steel and iron mass of the radial engine permitted a direct heavy lift connection. The crew successfully recovered the Bristol Perseus in 2011, physically reuniting the power plant with the surviving wings and forward fuselage. Once all the major sections were transported to the Aviation Museum in Norway, the engineering team faced a strict chemical timeline to stabilize the artifacts. The entire wreckage had survived decades submerged in cold, dark seawater. Low temperatures can slow some forms of decay, but seawater and trapped salts continue to drive corrosion over time. The moment these components are exposed to air, oxygen and drying concentrate the salts left on the surface, accelerating corrosion on surviving metal to slow post-recovery corrosion on the 905 horsepower engine and the duralumin airframe. Conservators typically keep waterlogged artifacts wet and begin controlled desalination. Freshwater baths are a common first step, with chloride levels monitored and the water changed in planned cycles to draw salts out gradually. Only after chloride levels fall to a safer baseline can longer-term stabilization and protective treatments be considered. The conservation plan is not about returning the aircraft to flight. The goal is a stable museum display, conserving what was recovered, supporting it where necessary, and making clear what is original and what is modern support. The final legacy of the aircraft is dictated by what can be preserved and safely presented from the material that survived the fjord. The preserved forward cockpit, the central wing structure, and the original recovered engine provide a permanent physical record of the 1940 strike mission. They demonstrate the exact structural tolerances of early wartime aluminum construction and the specific mechanical consequences of deep water submersion. The operation stands as a documented partial success. The engineering team successfully defeated the 794-foot depth constraint to save the main sections, and later executed a 1,230-foot extraction to save the primary power plant. The recovery permanently anchors the aircraft to its historical record, establishing a stable museum exhibit that accurately reflects both its combat service and its long submersion in the cold marine environment.